Hello, I'm Nitisha. I'm going to present a survey on task scheduling algorithms in energy harvesting embedded systems. These are the contents of my presentation. Ever since the computing requirements in the embedded systems have become ubiquitous, there is a requirement of self-powered devices which can supply the energy for, a, for the lifetime of a system. Energy harvesting is a process in which the energy is derived from external sources like wind energy, thermal energy, and stored for small wireless autonomous devices. Why energy harvesting? The driving force behind the search of energy harvesting is the desire to power the sensor networks and mobile devices without batteries. For sensor nodes to have a long lifetime, using conventional batteries is not advantageous. By tapping the thermal, light, or mechanical energy available in the ambient environment, energy harvesting is employed, which can run these devices without batteries. The first technique I'm going to describe is the earliest deadline with energy guarantee technique. This technique is introduced in order to enhance the performance of classical EDF scheduling algorithm. It runs tasks according to EDF, which is earliest deadline first. For EDEG algorithm, the task is considered to consume energy with any power such that energy storage is sufficient to execute this task during at least for one time unit, and the processor will remain idle when there is no sufficient energy in storage. The three major components of EDEG are E of t, slack energy, and slack time, where E of t is the energy that is currently stored at time t. The slack energy is the maximum energy that can be consumed from given time t while still satisfying the timing and energy requirements. And slack time at current time t is the length of longest interval starting at t during which the processor may be idle continuously while satisfying the timing and energy requirements. Coming to the performance evaluation of the EDEG, when it is implemented on discrete event simulator in C or C++, the performance of the techniques like percentage of feasible task sets, average idle time, and time overhead are compared and evaluated for low energy and high energy utilization. Under low energy utilization, the system is considered to consume little energy related to energy produced by the environment. When the percentage of feasible task sets which are feasible with EDEG and not with a greedy algorithm like EDS is experimented, the figure shows the processor utilization of 0.3, 0.6, and 0.9 respectively. When the processor utilization UP is 0.3, all task sets are feasible under EDEG when the feasible energy is around 7,100 units. The EDEG will benefit from the idle time to recharge the battery whenever the energy storage is insufficient to execute more tasks. On the other hand, EDS will need more energy storage than EDEG to guarantee feasibility, that is around 21,000 units. Therefore, EDEG can provide the same level of performance with a storage unit which is 4 times less. As observed for UP 0.6 and 0.9, the relative performance gain of EDEG in terms of capacity savings decreases when processor utilization rate increases. The schedule can be characterized by average duration of idle time intervals in a given time window. Lower the number of idle time intervals, lower will be the energy spent transferring the processor from inactive state to active state. The figure shows the comparison of total number of idle times of EDEG with two other algorithms. The average idle time of EDEG is greater since the total number of idle times is less. Coming to the time overhead from the figure under EDEG, for low values of processor utilization, the time overhead is low, and as the processor utilization increases, the time overhead increases. Therefore, higher the processor utilization, higher is the overhead. Similarly, for high energy utilization, from the graph of percentage of feasible task sets, the relative performance gain of EDEG in terms of capacity savings is decreasing when the processor utilization rate is increasing. And for higher processor utilization, the performance gain in capacity savings decreases. From the average idle time graph, the total number of idle time intervals in EDEG is lower compared to the other two techniques. For the high energy utilization, consuming energy increases the number of low battery levels. Thus, the number of idle times increases and consequently the average idle time decreases. From the time overhead graph, it is seen that the processor utilization increases the time overhead till it reaches a maximum value of 0.9. The time overhead for high energy utilization ultimately increases. The second technique I'm going to describe is the earliest deadline feedback scheduling with energy guarantee. It is a novel scheduling algorithm which is developed based on EDEG. It is mainly introduced to enhance the performance of EDEG. In order to evaluate the performance of this technique, rate of missed deadlines, average and minimum energy available are compared. The rate of missed deadlines is the ratio of number of instances of tasks that have missed their deadlines to the number of instances of all the tasks. From the graph, it is seen that the algorithm causes a small amount of deadline misses. The graph shows the average and minimum energy available. As shown in the graph, this algorithm saves significant amount of energy where average energy available is near to the maximum capacity of the battery. In order to enhance the quality of service, the energy-aware scheduling algorithms are proposed. There are two energy-aware scheduling algorithms, namely Green RTO Scheduler and Green BWP Scheduler. The Green RTO Scheduler is based on RTO, that is red task only, and EDEG algorithms. As defined previously, under EDEG, all jobs must complete before their deadlines, while under Green RTO, only red jobs have to be executed before their deadlines. The Green BWP scheduler is a mixture of BWP and Green RTO algorithms. Under this, the red jobs are executed in priority according to EDF rule, and blue jobs are executed whenever possible by taking both timing and energy constraints of red jobs into consideration. The difference between the RTO and BWP is that the slack time is computed only on the basis of current and future occurring red jobs in Green RTO, whereas in Green BWP, the sequence is also constructed upon the execution of the current and future occurring red jobs. The graph shows the QoS comparison for different values of processor utilization. As shown in the first graph, when battery energy storage is large, the Green BWP gives QoS performance that tends to 100%, and Green RTO gives constant QoS for all the processor utilization values. When battery energy storage is not very large, as shown in the second and third figures, the Green BWP and Green RTO still give an acceptable QoS in contrast to the EDEG. The utilization-based task mapping for multi-core systems has been introduced to achieve better efficiency in utilizing harvested energy. It selects the execution speed based on the CPU utilization, that is the lowest possible speed that is higher than or equal to the summation of utilization of all tasks. Since the energy dissipation of a core is a convex function of its utilization, it is proved that distributing the tasks to cores so that they have same CPU utilization minimizes the overall system energy. Coming to the performance evaluation, the graph shows the comparison of utilization-based multi-core algorithm with random partition algorithm and task moment algorithm with 3 and 4 cores. From the graph, it can be seen that for both 3 and 4 cores, the utilization task-based algorithm achieves lowest deadline miss rate compared to the other two algorithms, which is a great advantage to the UTB. In conclusion, the energy harvesting is one of the most promising solutions for increasing the lifespan of autonomous systems. Efficient task scheduling of energy harvesting embedded systems will help to reduce the deadline miss rates and increase the system performance. By using the energy-aware algorithms, issues like process overload and shortage of energy are eliminated. Also, the utilization task-based is best suited for multi-core systems with energy harvesting. While there has been extensive research on classical real-time scheduling, the real-time scheduling specific to the energy harvesting systems are just emerging. Thank you.